Record. Okay. There. As we were talking about, the final exam schedule is posted. We're almost at the very end, not the very last day, but the second to last day. I know. I'm sad about that as well. All my big classes, so you guys are a big class, and then I have another big class, and that marking takes a long time. And so both of them, I have one on the 16th and one on the 17th. I don't know how I'll pull it off, but I will. Like I said, it's in S104, so we'll be with multiple sections. And so closer to the date, we'll talk about what that will look like. But you'll want to make sure that you write my final exam because you're in my class and it'll be slightly different from the other classes. Okay, and so that'll be something to keep in mind, but it's still a little ways away, isn't it? Although we're getting there pretty quickly. I posted, let's see here, the new formula sheet, hopefully the final formula sheet, looks like this, and it's 2 pages. Yeah, make sure you grab the, oh, nice. And so there wasn't enough room to squish them all onto 2 pages, so they're across 3 pages. But how it works out is the test 1 material is on the first page. Then we have the test 2 material on the second page. And then finally, we have the stuff that will be new for the final exam on the 3rd page. And so it broke up kind of nicely anyways. Okay, I'll grab I made those changes that we talked about last day, right? Capital I equals PRT and oops, I want this here. So here's our new formula sheet. And last day we talked about compound interest, right? Adding an element where we're compounding the interest that we've earned or that we owe, right, at each compounding period. Okay. And so let's recall or review what each of these variables are, because they're going to come back to haunt us again today. Where A, bless you, is the accumulated amount or future value. Oops, that doesn't look like future. In both of these formulas, right, we have a P next. We also have an R and a T in both of these equations, as well as an N. Right? And so we have P, which is your principal amount. You have your R, which is the interest rate as a decimal. You have T, which is the time. Now, the interest rate and the time have to match, right? And then finally, N is the compounding frequency. As promised, last day, we had this equation, right? The future value equation, and we used it and we solved for P, right? I think we can all do that one. That one's pretty reasonable, but it's on your formula sheet just in case. right? And so there will be questions where you have to find the principal amount, right, instead of the future value. Or we also looked at solving for time, right? We use the natural log because a lot of, or all scientific calculators have an LN button, right? And so make sure you practice with the LN button, but besides that, you don't really need to know about logs in order to use the LN button. Yeah. And then finally, we solved for R, right? The interest rate R, which is n times the nth root of a over p and then minus 1. Or, notice how there's an or on here, right? If you prefer, how you're actually going to calculate this is a over p to the power of 1 over n times t and then minus 1. Okay? And so I'd say this one is probably a little bit more useful unless you have a fancy kind of tell it which root you want. Most calculators don't have that, right? And so this one is the best for most calculators, right? Where if we want to take the n times tth root, you raise the whatever you want to take the root of to the power of 1 over n times t. Right? So you don't need to remember that, it's on your formula sheet, but you do need to know how to use it, right? How to do it. That's important. And then finally, we introduce the effective interest rate. What's the effective interest rate? It's any interest rate compounding at any frequency n, right, converted to annually compounding, right? And so that allows us to compare interest rates. So here, it's the annually compounded rate equivalent to R at n, at n compoundings per year. That's from last day. Let's recall some common values of n, or common compounding frequencies. N equals 1 is annually. N equals 2 is semi-annually. Right, twice per year, annually. Ugh. We don't usually use n equals 3, but n equals 4 we do use. It's quarterly, right? 4 times per year. N equals, what's the next one? 4, 12? Monthly. I forget one. Oh yeah, I'm trying to work through them in increasing order so I don't forget one, but there is, yeah. N equals 26 is bi-weekly. N equals 52 is weekly. Oops. And n equals 365 is daily. We know that there could be more than 365 per year, but we just always use 365, right? If there's a leap year, we don't care. We just always use 365. These, you should remember these, but this isn't really math, is it? So if on the test you're unsure, just ask me. okay? And so it'll say compounding monthly. And if you want to just double check, hey, does that mean n is 12? You can do that, okay? But once you use them enough, you'll start to remember them, right? Because we need n in all of these formulas, right? If you go through and you have a compound interest problem, right, then you'll need n in every single formula, right? So it's pretty important. Yeah. All of these scenarios, or the scenarios that we've seen in simple interest, right, and in compound interest, we have pretended that we've had some amount of money and we go to the bank and we deposit it, and then we let it grow, we let it sit there for some amount of time, and then after some amount of time, we say, hey, give me my money back and my interest, right? And that's what we've been solving for. But we also know that a lot of the time we have payments, right? You take out a car loan, for example, right? Then you're making regular payments, paying off your loan, right? You can also make regular payments into a savings account, okay? But today, we're talking about what we call annuities and sinking funds. And so annuities is going to be a really important part of this. And then sinking funds is just a special case of annuities. But annuities are where we make regular payments, right? And by regular, I mean monthly payments or maybe annual payments, right? Daily payments. That's crazy. But weekly payments maybe. And so where we make regular payments into our savings, our savings, or to pay off a loan. Let's see here. I'm going to add a page. Oops. I'm going to go to our formula sheet that you have in front of you now. And notice that the only section that I give you until we hit sets and counting, which is the next chapter, right, is called ordinary annuities. And so here, ordinary annuities are going to be quite important. And so here, which means we need to know what that means, right? What does ordinary mean? Well, we just decided that an annuity is where we make regular payments, right? Monthly payments. I'll say, for example, monthly car payments, something like that. But what does the ordinary mean? So ordinary annuities, but I want to talk about the ordinary part. So the ordinary part means that the payments that you're making, usually we're making these payments, right, either to pay off a loan or to create savings, right? But either way, we're making payments. Okay? The ordinary part means that we're making payments at the end of the payment period. Okay? So at the end of each month, at the end of each week, right, at the end of each year. Okay? And so the ordinary in this case means we make our payments at the end of the payment period. So for example, at the end of each month. Now the thing is, in this course, all our payments will be at the end. I have a little blurb about if payments are at the beginning of the payment period and what changes, but I'm not going to test you on it. Okay. And so on the test, so on test 2 and on the final exam, we have ordinary annuities. Okay. Meaning payments are at the end. So I'll say that here. On test number 2 and the final exam, we will only consider ordinary annuities. Also, if a question is unclear whether payments are made at the end or at the beginning of a payment period, you can assume it's at the end. They have to say if it's at the beginning. And so if a question is unclear about when payments are made, at the end or at the beginning, right? If it's unclear, so if it doesn't say, we can assume it's at the end. We can assume payments are made at the end. Today, we're just going to talk about the future value. Okay? And so this is today. And this we'll save for Monday. Something to look forward to. I know what you're thinking. Isn't this just the same thing here? It is. And you know what this is? This is just compound interest, the A for compound interest. So we've already seen, so come Monday, we'll have seen these formulas, then we're just putting them together. Okay? And so it looks terrible. It does. I'll give you that. But it's not going to be too bad. But we do need to tackle this mumba jumba today. Mumba jumba, is that a real term? I don't know. It's big. Okay, so ordinary annuities. We're making regular payments. Okay? And the formula that we'll use, let's see here. I'll bump this up here. I'll grab the one from your, this will be the same as what's on your formula sheet, right? But we introduce a new variable, m, a lowercase m. Okay? So if a payment of $M, okay, so that regular payment, let's say you're paying $300 a month for your car, right, to pay off your car loan, right? Or maybe you're saving $200 a month or something like that, right? Then M is going to be that $200 or $300, right? That payment amount. And so if a payment of M dollars is made in an account N times a year at an interest rate R, then the final amount A after T years is given by this formula. Now, if we kind of take a step back and focus on this 1 plus R over N to the N time, N to the T, or N times T, I should say, right? That looks kind of familiar. We've worked with a formula like that before, right? For compound interest. And then we're subtracting 1 and we multiply by the M and then we divide by R over N. Yeah? And so the future value is still often called the accumulated value, which is why we use A in this case. Yeah? Now, I think there's a, yeah, here. I'll move this up here. Notice that the formula assumes that the payment period, right, because a payment of M dollars is made into the account N times per year, which means N is also our compounding frequency, right? And so what we're saying is that the payment period is the same as the compounding period. If they're not the same, then we can't use this formula anymore. Okay? There are other formulas, but we're not going to introduce them in this course. Okay? You'd have to take Math 114 with Claude next door, right, to see the other formulas. They exist, of course, but we won't use them. And so we're talking about kind of a very specific case in this course, but it's enough because it's the most common case. And so here in this course, they will be the same. We're still going to keep an eye out for that, right? The frequency that I make my payments at has to match my compounding frequency, right? And so we will still be sure to check Okay, it sounds like they're doing what we did last day. So we will still be sure to check that the payment frequency matches the compounding frequency. I'll say they will, but it's good practice. So I guess we'll confirm. Now, when we're making these regular payments, really what happens, I'm going to close the door. All of a sudden, close so loud. Blogs. Maybe I'm just getting distracted. What are they doing over there? Visually, what's happening when you're making payments? Let's say that you're saving money, right? And so, as an example, right, say you are saving $200 per month for 4 years at a rate What's kind of a reasonable rate right now? Pretty low. It's very, very low. Let's say 2%. I know that's even high right now, but at a rate of 2% compounded monthly. Okay. How much will you have in your account at the end of the 4 years? Okay. So how much will you have saved at the end of 4 years? I need to make more room. Oh, I have a page. Let me just. Oh, that's confusing. Move these down. Just little guys. We can solve this even without the formula that we introduced, right? And so I want to show you that we could do it, and then you'll appreciate the formula so much more because it makes it a lot easier. Okay? And so what would you have to do? If we draw this out, we can always sketch these out, especially when we're making regular payments. We can pretend that here we are today on this timeline, and here I am 4 years from now. Okay. At the 1 month mark, I'm going to deposit $200. And then at the 2 month mark, I'm going to deposit another $200. And then I keep going for 4 years, which is, let's see how many months. 4 times 12 months is 48 months. So I'll do that up here. 4 years is the same as 48 months. Which means before that I was at the 47-month mark and the 46-month mark. Right, and it just keeps going and going and going. And at each month, at the end of each month, I deposit $200. Without the formula that we have introduced just briefly, right? What would we have to do? You would have to take this $200. Oops, let's make it nice and big here. And find the accumulated value, right? And so here, this is your P, 200, and you would need to find the accumulated amount. I'll say A47 for the 47th month, because each payment that you make is going to have its own A, right? And so you would find the accumulated amount after 1 month, right? Because it only sat there for 1 month. But this guy sat there for 2 months, right? So it'll be a little bit bigger. Oops, 46. This guy sat there for 46 months, right? Because it was deposited at the 2 month mark, right? And so in between here, every single month has some accumulated value at the end of the 4 years. So A2 and A1. That's very tedious. You'd have to find A 47 times because the A for the 48 is just 200, right? It was just freshly put in, so it doesn't move. Okay. But this is what we call a time diagram. We're not going to use them a ton, right? But it is nice to see what's happening. Okay? And so here, this would be, if you add those all up, This is the total accumulated amount. And I'll say after 4 years. As we've seen, though, we don't have to do this anymore, right? But it does explain why our formula has to be a little bit more complicated, right? Because we have to incorporate that this $200 sat there for only 2 months, right? Whereas this $200 sat there for 46 months, right? And so we have to take that all into account. And maybe I'll add that here. It sat there for 1 month, it sat there for 2 months, sat there for 46 months, and this one sat there for 47 months. So they're all sitting there for different amounts of time. And of course, we know that if I deposit $200 and it sits there for 47 months, it's going to be worth a lot more than $200 that only sits there for 1 month, right? So they all started at 200, but then they all had different times to grow. So luckily, we have a formula to use instead. Aren't you glad? You could do it for kind of shorter payments, right? That's totally fine. You'll find the same answer, but for longer kind of payment plans like cars, usually cars you take what, 4 years to pay off? Usually houses you take 25 years to pay off, right? And so you don't want to be making a time diagram like this for 25 years with monthly payments. Ugh, no thanks. So that's why we use, and maybe I'll use the one on our formula sheet so that we get familiar with seeing it. It's the same as what's on your in the textbook. And we do want to highlight here that M is the only new player, right? We're familiar with R. In fact, we're familiar with R over N, right? It's your rate divvied up over each of the compounding periods, right? N times T, we've seen that before. R over N, again, almost tedious. So where M is the payment amount. Let's do an example. If at the end of each month, a deposit of $500 is made in an account that pays $800 compound, sorry, $800. I don't know where I got that from. I guess it's a 800 if you read the percentage weird. 8% compounded monthly. What will the final amount be after 5 years? And so we want to find A. And what are we given? We're given that it's at the end of each month. And for us in this class, like I said, I'll introduce how you solve problems where it's at the beginning. But for us, right, we want to make sure that, okay, payments at the end. Dink. If it doesn't say, then you can assume it's at the end. Right? It's only at the, if it's at the beginning, they have to say. And so M must be $500, right? That's that payment, that regular payment that we're making, right? And so that's what makes it an M. R is 0.08 and N is 12 monthly. And the payments were made monthly. Make sure these are the same, which they are. And then finally, we're given our T is 5 years. Remember, for compound interest and now for annuities as well, T has to be in years. So if the time is given in anything but years, you have to convert it, right? So if it's 10 months, then that's 10 over 12 years. Right? Okay. Let's solve this thing. We've got A equals M times, let's see if I can remember, 1 plus R over N to the N times T minus 1 over R to the over N. Let's see. M 1 plus R over N to the T minus 1 over R over N. Phew. Nice. Nailed it. We want to solve for A, that's nice. And we have M is 500. Plugging in our values, 1 plus 0.08 divided by 12 to the power of 12 times 5. Oops, clean this up. Then minus 1 over 0.08 divided by 12. I see that I have this 0.08 divided by 12 in here twice. And so what I'm going to do is I'm going to see if this makes a nice number, right? A non-repeating number that I can just replace it with. Okay. And so 0.08 divided by 12, it's not nice. 0.006666666666. So what I'm going to do instead, to make sure that I keep all my decimal places, okay, is I'm going to store it in my calculator. Okay. And I am confident all your calculators have a store function, right? Most scientific calculators have a store function. Okay? And so let's see here. I've talked about the store function before, but for money, it's going to be really important, right? And so here, I'll do it in red even. It's really raining. Thanks. We need to keep all decimal places. I'll say use the store function. STO is usually what it says, okay? But it stands for store. The store function on your calculator. And so what I'm going to do is I'm going to say, hey, I've calculated this. It wasn't anything nice. I'm going to store this in A. Okay. Just to indicate that, yes, I am storing all my decimal places no, I don't want to write them all out because it's really tedious, right? And so let's see here. I'm going to rewrite this 500 times 1 plus, and then you can write store in A, or depending on your calculator, you might store in 1, 2, 3, 4, right? And if you want my help figuring out the store button on your calculator, right, then let me know. But store in A, and then 12, oops, I forgot to store in A. Store in A, there. 12 times 5 simplifies to 60 payments, then minus 1 over store in A. So here I'll highlight this because that's something you'll want to work on. Okay. Now what? To simplify this, all of this, right? You can simplify the numerator and the denominator separately, but we've already simplified the bottom, right? The denominator. And so now let's simplify the numerator, right? The numerator is the numerator because it's numero uno, so it's on top, right? And so the numerator needs a little bit of work. What do we need to do next? We need to take 1 plus whatever is stored in A, right? Then I need to raise it to the power of 60. Then I need to subtract 1, and then I need to multiply by 500. Okay? You do not need to write out all these steps because that's a waste of time. Okay? And usually, right, once you have enough practice, then you know that you're going to take your r over n, then add 1, then to the power of n times t, then minus 1, then times m, and then finally divide by the bottom, right? And so that's going to be a lot easier if you just do it on your calculator, right? But you want to do it in the right order. So to encourage you to do it in the right order, I'm going to write it out with each step one by one. Okay? And so here, and I'll even highlight what it is I'm going to do next here. I'm going to add this here, which says that A is 500 times 1.0066, repeating. Oops. Recall A plus 1 to the power of 60 and then minus 1 divided by whatever is stored in A. Next thing I'm going to do is I'm going to take this 1.0066 repeating to the power of 60, which is still on my screen on my calculator, right? Which is how I avoid having to store stuff most of the time. And so to the power of 60, we get still 500 on the outside times 1.48984578 ... because it does keep going. But I can't see anymore, but I'm going to make sure I keep all those decimal places. Then minus 1, oops, divided by whatever is stored in A. Now minus 1 on my calculator. A is 500 times 0.4898457083 ... divided by store. We're getting close. Now, times that by 500. Whoops. Times 500. Get 244.9228542 divided by whatever is stored in A. Now I can take this, my last step. A is going to be whatever's on my screen divided by recall A. And I get 36738.42812. My pen is glitching. A is money, which means that at the very, very end, I can round to 2 decimal places, right? But not until the very end. 738 and 43 pennies. We get $36,738.43. Nice. Good. Kind of tempted to see well, in this case, we would round up so you'd end up with more money, but that's not what happens. Usually it would mean you'd have to pay more money. That's bad, right? If we hadn't kept all the decimal places. You can try it with some other number, right? If you rounded this to 0.0067, for example, right? And see what you get, right? But the dollar amount that it should be is this one here. It'll be different if you round. Okay. How about another one? Tanya deposits $300 at the end of each quarter in her savings account. If the account earns 5.75% compounded quarterly, how much money will she have in 4 years? Okay. Looks very similar to the one we just did. Right, and so let's see here. We want to find how much money. We want to find A. And we're given it's at the end, which is what we know how to deal with. Right? M is 300 quarterly. And R is 0.0575 and N is quarterly, which means it's 4. I did it weird. Let me just clean this up. N is 4, which means it's quarterly, which means that the payment frequency and the compounding frequency are the same, which means we can move ahead. Right? They will be the same, but just want to make sure. And finally, T is 4 years. And for compound interest and annuities, T has to be in years. Right? And so that's good. Lots to keep track of. But we want to find A, and we have a formula for A, which takes into account our regular payments, our quarterly payments. So now we're ready to go. A is n times 1 plus r over n to the n times t minus 1 divided by r over n. Feeling pretty confident about it now. That formula. Yeah. Be too bad if I memorized it wrong. It's on the formula sheet. You don't have to memorize it. Okay. Now it's a matter of just plugging in the values. Right? And so we have M is $300 times 1 plus 0.0575 divided by 4 to the power of 4 times 4, then minus 1 divided by 0.0575 divided by 4. Let's see if 0.0575 divided by 4 makes anything nice. It does. That's nice. Right? So let's do that as our first step. I'm going to replace 0.0575 divided by 4 both times with 0.014375 because it's nicer to look at. And so keeping everything else the same, 1 plus 0.014375 to the power of 16 minus 1. You can simplify that 4 times 4 if you want. In fact, you're allowed to skip from here all the way down to your A, right? The calculated A. And so I'll make a note of that here, but I just want to show the calculations step by step again. Yeah. So I have 0.014375 on my screen. So my next step is adding 1. So here I'm going to deal with this guy next. So A is 300 times 1.014375 to the power of 16 minus 1 divided by 0.014375. Oh, I need a page, and I'm going to actually move this up here. There. So this one. Then to the power of 16. Making sure that we do this in the right order. $300 times to the power of 16. 1.256548 minus 1 divided by 0.014375. Next, minus 1. .256548 divided by 0.014375. We're on the home stretch now. Times that by 300. Make sure you keep all your decimal places. I get 76.96223999 ... because I don't know what happens next. Then divide that by 0.014375. Finally, do this division. 0.014375. I get 535.894956. It keeps going, but I only need 2 decimal places. 53.89. Clean this up. To 2 decimal places, right? When it's money, you round to 2 decimal places. Yeah.
So we don't have to like write off the entire investment. Whatever shows up on the calculator.
Yeah. Yeah, so as long as you make it clear to me that you understand that it keeps going and that you've kept whatever's in your calculator, because the calculator shows, it can usually only show 9 digits, and so often, and so, but it has more in memory. Now, in terms of showing your work, I know you're going to be so excited here. You can go from here at the very top down to here if you want. What? I know, crazy, right? So here, you don't have to show me all these steps. I know, weird, right?
So I just like rounded it up, like right by. It regards to that.
Oh, okay. That's okay. So some of them show fewer. That's okay. I'm just writing out all that I can see, and yeah, I haven't counted recently how many I get, but just make sure that you're not clearing it and trying to enter it again. Just keep it on your screen and use it.
So sorry, like what were you saying? For like the exam, can we just like plug the entire thing into the answer?
So here, what I'll be looking for is first the empty. I want to see the empty formula so that you show me that, hey, I know I have to use this one, right? And then here, you're showing me that this is what I'm going to be entering here. And then if you show me your work, right, then I can save some marks if you do something weird, right? If you do some illegal math, right, like maybe you take maybe you do it in the wrong order and you take this number to the power of 16 and then add 1, that would be wrong, right? But if you showed your work, I can give you more, I can kind of give you more part marks, because then I can see where you went wrong, right? But at the end of the day, right, if you kind of are on a roll with your calculator, you can skip straight from here to here. Ultimately, it will result in the same amount of marks, right? Because if you don't end up with the right answer, I'll know you did something weird, right? Some sort of illegal math happened, and yeah. So usually the marks end up being the same anyways. So, but it's nice to be able to show your work then if you're unsure, but if you're feeling confident, all right. And maybe I'll do here this and this is the only work that must be shown for full marks. All right. All the rest, I can't even have it on one screen here. All the rest, let's see if, what happens if I turn this? I'll do it. Whoa. Oh, it's so small. Hard to see, but all the rest is extra.
When it comes to this, this, we just like cut it off there, we just don't like round it out.
Here,
Yeah, so.
I'll turn it again. At this point, because I'm about to round to 2 decimal places, I kind of stop caring, right? But as long as you get to this point and you get the right decimal at the very, very end, you did it. Okay. Nice. Any other questions about that one? Especially about showing work, stuff like that. How about this one? Here's a different one. Robert needs $5,000 in 3 years. That can happen, right? We have savings goals, right? And so how much should he deposit each month in an account that pays 8% compounded monthly in order to achieve his goal? Right? That's kind of an interesting problem. So what is it that we need to find? How much should he deposit? We want to find M. That's a new one. What are we given? We're given that the accumulated amount at the end has to be $5,000, right? So $5,000 in 3 years. I'll just do the monthly and the monthly here. So he's making some unknown payment amount that we're going to solve for each month in an account that pays R equals 0.08 with an N of 12 monthly. We have our formula. And we only have this one. But if we have A, we've been solving for A given M before, and now I want to solve for M, but I'm given the A, and so I'm really only missing one piece of information still. And so here, 1 plus R over N, there's one downstairs. To the power of N times T minus 1 divided by R over N. We want to solve for M. We know how to do that. Right? I was mean and I didn't put it on your formula sheet, right? But once you've simplified all of this, right, then it's an easy solve, right? Because then you just have to take A divided by all of this. And I think it's almost easier to do that once you've simplified instead of doing the proper formula for it. So I want to force A to be $5,000 on my savings goal. I'm solving for M. And I have 1 plus 0.08 divided by 12 to the power of 12 times 3 minus 1 divided by 0.08 divided by 12. Let's see if 0.08 divided by 12 is anything nice. It's not. They love these nasty, nasty rates. Okay. I'm going to store this in A. Because I'm on a new question, right? And so if you store stuff and then if you store it in A again, it'll just overwrite it, right? So you can just, usually I just always store stuff in A and then forget about the rest unless I need them. And 12 times 3, let's simplify the 12 times 3 is going to be 36. And so I have 5,000 is M times 1 plus whatever's stored in A to the power of 36 minus 1 divided by whatever is stored in A. Okay, I hadn't actually stored it in A, so I had to do that first. But now I have to add 1. No, I should do it properly. 1.066 repeating to the 36 minus 1 divided by stored in A. To the power of 36, I get 5,000 has to be M times 1.270237052 minus 1 divided by what's stored in A. M times, I'll use square brackets still, 0.27023705516, then divided by store in A. Now, there's a couple of different ways that you could do this. Okay? You could simplify this number, right? Because it's all multiplying and dividing, the order doesn't matter, right? Alternatively, what you could do is, I'll undo this, is multiply 5,000 by what's stored in A and then divide by 0.2703, blah, 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 blah. Right? Making sure you keep all those decimal places. I find that that's more confusing, right? Because it involves 2 moves, right? Whereas if I simplify, right, the 0.27 whatever divided by store A, that'll be just one number that I can divide into 5,000. So I'm going to use that method, but it wouldn't be wrong to use the other method. Oh, and I guess I should keep circling what I did at each step. Okay. So now divided by recall A, 5,000 is M times 40.5355774. Keeps going. I can't see it. Which means that M, solving for M, which is what I want to do, I have to divide 5,000 by 40.5, blah, 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 blah. So I'm going to do 5,000 divided by my previous answer, and I get M must be 5,000 divided by 40.535555774, blah, 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 blah. So M must be 123.348494. M is a dollar amount. $123.35 rounded to 2 decimal places. I'll highlight again for full marks. you would show me this. So if you show me your empty formula with the numbers all filled in, then as long as you end up with the right answer, now I want to see the unrounded values, right? And then the rounded values. It's not until the very, very end that we get to round. Nice. Any questions? No. How am I doing for time? I never know. Usually I'm pretty good at knowing in the daytime. In the nighttime, I guess I can't tell. I don't know what it is. Okay. Yeah, sorry.
So this one, without 35,
Yeah, so here, the 9 was followed by a 4. And so it has to be followed by 5 or higher, then you round up. Okay? And so if this was 895,956, then you would have to round up this 9 and you would get to 90 cents. Right? Whereas here, because the 4 was followed by 8, right, then I have to round to 5. Okay. You know what? I did write that a bunch on the test, so I'm just going to make a note of the rounding here. And so here, or maybe I'll use a different color. To round to 2 decimal places properly, we look at the second decimal place, or maybe I should say the third decimal place. If it is 5 or higher, we round the second decimal place up. We round the second decimal place up. And then if not, then you keep it as is. Let me make some room here. If not, keep the second decimal place as is. I made it capital 2. There. Good. So what we just did, if you want to get fancy, you can call it a sinking fund. In business, they call it a sinking fund. I'm convinced it's just to make them sound cooler, but it's really just a savings account where they're trying to save for some future amount. And so when a business deposits money at regular intervals into an account in order to save for a future purchase or equipment, the savings fund is referred to as a sinking fund. Doesn't really make sense to me, but that's just the name of it. I guess you're sinking money into the fund. I don't know. Calculating the sinking fund deposit uses the same method as the previous problem, which we saw above. So, in a similar problem, let's move this down. Bigger monies though. A business needs $450,000 in 5 years. That can happen. How much should be deposited each quarter in a sinking fund that earns 9% compounded quarterly to have this amount in 5 years? And first things first, we need to make sure our payments, they're quarterly, which means our compounding also has to be quarterly. And that's true. So that's good. And how much should be deposited? We want to find M again. And so here, really, a sinking fund is really solving for M, which we did earlier as well. Just a fancy special case. We're given that A has to be $450,000. T, we have 5 years to do it. And T is in years, which is a little check mark. Yeah, sorry.
Will we have to like look for R or N, or sorry, find R or N?
No, no. For annuities, we're gonna solve for P later, next on Monday. We're gonna solve for A, which we've done today, and M, which we're doing now. And that's it. The other ones, way too hard. Let's see here, 5 years, each quarter, so N is 4 quarterly. And R is 0.09 quarterly. Oops, I shouldn't have written this quarterly there. We have everything. A is M times 1 plus R over N to the N times T minus 1 divided by R over N. I need A to be 450,000. I'm solving for M, so I leave it empty. 1 plus 0.09 divided by 4 to the power of N, which is 4 times T, which is 5, and then minus 1 divided by 0.09 divided by 4. I hope 0.09 divided by 4. Come on, big money. It's a nice number. Great. That'll save us some writing. Now what I'm gonna do, 450,000 is annoying to write out. So if something's not changing on one side of the equal sign, then you can just leave it blank. All right. M times 1 plus 0.0225 to the power of 20 minus 1 divided by 0.0225. M times 1 to the power of 20 minus 1. I'm gonna add a page. Takes way longer if you write it out than to just calculate it. Plus 1 to the power of 20. I'll do the 450,000 because I'm on a new page. M times 1.560509201 minus 1. Oops. Divided by 0.0225 and minus 1. M times 0.560509207 oops, divided by 0.0225. I like to do this division, right, and then divide over. And because I'm about to work with the 450,000 soon, I'll start bringing it back in here. M times divided by 0.0225. 24.911520003. M is 450,000. I don't know why my pen is just gapping out. It's bad. It's happened to me before, and I had to get a brand new pen. I hope that's not true this time. Maybe I need a new nub. Start there. A new nub on my pencil. I don't think I've ever replaced this one, so it's pretty good. Okay. M, I get 450,000. Make sure you have all your zeros. Oh my gosh. I just deleted the 2, 4, 9, blah, 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 blah. Let me do it real quick. 1.0225 to the power of 20 minus 1 divided by 0.0225. Phew. Back where I started, but I won't pause. 18063.93185. Now, because the 3 is followed by a 1, right, or because my second or my third decimal place is less than 5, I just keep my second decimal place as is. 93. That's a lot of money to be depositing every 3 months, right? Quarterly is every 3 months, but they are trying to save almost $500,000. So I guess it's gonna take some monies. Yeah. Pardon? No, it's a tricky one because it's 4 times per year, but 4 times per year is every 3 months, and so I know it's one of those confusing ones. Let's think about it this way, though. They made 20 payments, right? Quarterly for 5 years. So they made 20 payments of $18,063.93. So how much money did they actually pay in order to get this 450,000? Let's see here. I'll just do a little side note here. Versus M times 20, which is 18,063.93 times 20. So in terms of money that they had to put away, and actually give $361,278.60, right? But because of the time value of money, is what it's called, right? Where we are able to deposit and earn interest, right? Then that's how they're able to get to the final amount of 450,000. So that's nice. Means you have to have 18,000 every 4 times a year, but still, campers.
Uh,
Oh, the 20 is from n times t equals 20 payments. Really glitchy. Yeah, sorry. Solving for m will be, but not this part. Yeah. Yeah, you'll need to solve for m on the test and probably on the final exams. Okay, let's see here. I do have this one, but just as you've probably noticed, in this chapter, there's a lot of topics that I'm not going to test you on, right? It's just good to know that they exist. Okay? But from here on down, not tested. Okay. And so that's why it's not on your formula sheet either, because I didn't want you to get confused. But an annuity due is if the payment is made at the beginning of each period. Okay? And so now at the beginning of each month, if we think about our original timeline that we made, whoa, a long time ago, so much math happened. All right. If I copy this, paste. Now for an annuity due, oh, and maybe I'll do this. Copy and crop. There. And then I'll paste this down. And clean this up. I'm getting there. Hey. Now for an annuity due, what happens is that this $200, I put it at the 1 month mark, right? That's at the end of this month, right? And so what happens is just minor, but all of these payments get shifted back 1 month, which means they get to stay there for just 1 month longer, right? Earning a little bit more interest for 1 more month, right, than they were before. And so it does mean that we have to adjust our formula a little bit, but nothing too crazy. In fact, the formula looks like this. This looks the same. All right, I'll zoom in even more. M times 1 plus r over n to the t, but plus 1, right? Because we bumped everything to the front, and so now it sits there for nt plus 1. And then the minus 1 is the same over r over n, that's the same. And then we have to subtract a payment from the very end. So, but besides those two changes, everything else is the same as before, right? But that's how we adjust for those payments being bumped back 1 month, right? Because now instead of 47 months, this payment of 200 sat there for 48 months, right? And everything got shifted. Okay. Let's see here. I will highlight this. we mentioned the formula for the annuity due only for completeness, right? And that's why I'm not testing us on it. Right? It'll be an ordinary annuity, which we've already seen today. But let's do just a quick example, and then we'll be out of here. Because that's all I've got, I think. Yeah. If at the beginning, so like I said, if it's at the beginning, it has to say in the question, right? If it doesn't say, if it's unclear, you can assume it's at the end, right? Because that's what we know how to work with. But let's just try this formula one time and see how it goes. If at the beginning of each month, a deposit of $500 is made in an account that pays 8% compounded monthly, so that's good, these match. That still has to be true, right? What will the final amount be after 5 years? So we want to find the final amount. We want to find A. And we're given, okay, we're given it's at the beginning this time. And M is 500 per month. R is 0.08. Compounded monthly, so 12. And T is 5 years. And again, make sure that T is in years, but it will be. Okay. So now we adjust our formula just a little bit. M times 1 plus, my pen might die before we finish. N to the T plus 1 and then minus 1 over R over N minus M. Let me double check here. M times 1 plus R over N to the NT plus 1 minus 1 R over N minus M. So when it's at the beginning, we have to make that adjustment. Again, I'm not testing you on it, but there are homework problems on it, right? So we should see it one time. I want to solve for A. M is 500 times 1 plus 0.08 divided by 12. A. Why is it? Let's see if maybe it needs to pair or something. Maybe that is it. 12 times 5 plus 1, then minus 1, divided by 0.08 divided by 12, minus 500. Let's see, 0.08 divided by 12. It's bad again. It's the same bad one. They love it. Fine. I'm going to store it in A. Even though it's already stored in A, isn't it? Probably from before. 500 times 1 plus the storage in A. 12 times 5 is 60 plus 1 is 61. Then minus 1 over what's stored in A. Then all that minus 500. You might find it helpful to put brackets around this and then minus the 500 just to remind yourself that you want to do that at the very, very end. Okay, now we're ready to move here. A is 500 times 1 plus recall A. 1.066 repeating to the power of 61, then minus 1 divided by stored in A, and then minus 500 to the power of 61. 1.499778013 minus 1. Oops. Minus 500. $500 times 0.499778013 by store A times 500. Getting close. 249.889065 divided by store A minus 500. Recall A. A is 37483.35098 minus 500. Since we bumped that last payment to the previous month, 35098. Finally, 3698330. Oops. 35. $36,983.35. You have any questions? Let me know. Otherwise, enjoy your weekend. I'll see you on Monday. Stop this recording here. Uh-oh, there was a